Back Chemistry 30, this is the EQ2.3 solubility section. So in EQ 2.1, 2.2, we saw what solubility was, looking at the maximum amount of solute that can dissolve in a solvent, and then we looked at saturated, unsaturated, supersaturated, and then we looked at factors that affected solubility. So now we'll look at, given the KSP, molar solubility or solubility, calculate the other two quantities. So dissolution or dissolving and precipitating, so going back into a solid, occur both within us and around us. Tooth in animal dissolves in acidic solutions, for example, causing tooth decay, and precipitation of certain salts in our kidneys produce kidney stones. The waters of earth contain salts dissolved as water passes over and through the ground. Precipitation of calcium carbonate from groundwater is responsible for the formation of stalactites and stalagmites within limestone caves. Now, back in physical science, we looked at precipitation reactions, and we used a solubility table similar to this. It was a little bit different than this, but very similar, looking at what combinations of a positive ion and a negative ion would result in potentially forming a precipitate. In other words, something that, for the most part, is not going to be soluble, not dissolved, so it's going to stay as a solid. And when we did that back in Physical Science 20, they gave us a qualitative sense of whether a compound has a low or high solubility. So just gives us an idea of whether it's soluble or insoluble. By considering solubility equilibria, however, we can make quantitative predictions. So actually calculations and figuring out numerically what is happening with solubility. So this leads us to the solubility product constant, or KSP. The ESP stands for solubility product, and the K represents, of course, an equilibrium constant. So recall that a saturated solution is one in which the solution is in contact with the undissolved solute. So for example, a saturated solution of barium sulfate in contact with solid barium sulfate. Because the solid is an ionic compound, it is a strong electrolyte and yields ions when dissolved in water. And it establishes the equilibrium. So if we imagine this, if we had a beaker here with water, and if we had some barium sulfate on the bottom, solid. So of course some of it would dissolve and some of it would recrystallize. So here you have the equilibrium. Solid going to ions, solid going to ions, and then ions coming into contact with the solid and forming solid again. So that is this direction. So this equilibrium is established that like that. And of course, AQ, aqueous, and of course that means dissolve in solution. Okay, and then of course we have the solid. So this pictorial here represents that equilibrium. As with any other equilibrium, the extent to which the dissolving happens is expressed in terms of how big the equilibrium constant is. Because the equilibrium equation describes the dissolution of a solid. The equilibrium constant indicates how soluble it is. So if you recall before, KEQ equals products over reactants. So if we get a big number, that means there's a lot of products compared to reactants. So the larger the K value is, the more products are, or in this case, the more dissolved ions there are. Okay, so this is called the solubility product constant, or simply solubility product. It is denoted as KSP, where SP, of course, represents solubility product. The equilibrium constant expression for the equilibrium between a solid and an aqueous solution of its component ions is written according to the rules that we did before. Remember, however, that solids do not appear in the equation. Because remember, that's a heterogeneous equilibrium. And the solid will not change drastically compared to the aqueous ions. So again, we only include those substances that aren't solid or pure liquid. So in this case, the AQ. So the solubility product is even easier. It just simply contains the product ions. So only contains product ions. So it's relatively easy. And of course, if there's an exponent, if there's a numerical coefficient in front, that becomes an exponent. So in general, the solubility product, KSP for a compound, is the product of the concentration of ions involved in the equilibrium, and again, each raised to a power, because really what we're doing here is we're figuring out a probability. If we have two of these, we multiply them by each other, so it becomes an exponent for simplicity. The coefficient for each ion in the chemical equation also equals its subscript in the chemicals formula. All right, on the next page, the values of KSP at 25 degrees C for many ionic solids are tabulated and can easily be found. So if you Google search KSP values, you can easily find them. And most of them are around a certain temperature, because they can be different at different temperatures depending upon whether the reaction is exothermic or endothermic. So for example, the value of KSP for barium sulfate is 1.1 times 10 to the minus 10. And of course, that's a really, really small number. And that, of course, indicates that if it's a small number, that means a very small amount dissolves in water. So a very small amount exists as an ion form. All right, let's look at this example. Write the expression for the solubility product constant of calcium fluoride. So calcium fluoride, we would show that being dissolved in water. Now, of course, calcium, in your pink periodic table booklet, that's 2+. Fluoride, of course, is a halogen, F-1. So calcium fluoride breaks down to calcium ions floating around in solution and fluoride ions floating around solution. And of course, these are ions, so you don't use the Hofbrinkel rule thinking that it's F2. It's an ion. It gets broken apart. So it's like calcium fluoride is getting dissolved in water. So it's breaking apart into what you see here. For every one calcium, there's 2 fluoride ions. So you imagine that happening. And of course, to show fluoride ions, we don't usually write F minus plus F minus. We write it as 2F minus. Okay, and of course the solubility product constant, we would not include the solid, but we would just include the ions. Square brackets, of course, indicate molar concentration, and that's what we would get. So relatively easy there, ladies and gentlemen. So calcium ions multiplied by fluoride ions, and it's to the exponent of 2. All right. Solubility and KSP. It is important to distinguish between solubility and solubility product constant. If we recall in the last section, solubility is the quantity that dissolves to make a saturated solution. So that maximum amount that dissolves to give a saturated solution. Solubility is often expressed in terms of grams per liter in everyday sense. In chemistry, we talk about molar solubility, which is how many moles of solute are dissolved per liters of solution. And the solubility product, which we've been just talking about, is the equilibrium constant for the equilibrium between the solid and its saturated solution. And we don't include a unit there, it's just simply a number. And of course, the size of it, or magnitude, tells us how much the solid will dissolve. So it tells us if most of it dissolves or some of it dissolves if it's a small number, etc. Solubility of a substance can change considerably in response to a number of factors. For example, solubilities of hydroxide salts, such as magnesium hydroxide, are dependent upon the pH, as we'll see in the next unit. The solubility is also affected by concentrations of other ions. In other words, common ions, and we'll see that in the next section, 2.4, what that means. In other words, the numerical value of the solubility of a given substance can and does change if there are other things being involved. In contrast, the solubility product constant has only one value for a given solute at a specific temperature. Okay? So the solubility could change, but the KSP value is going to remain constant. All right, I think we'll stop right there, and then we have about 3 examples to do, and then you'll be able to do the assignment. So we'll see you again.